Alright, friends, I'm watching this video, I think for the 5th time here. Very stimulating. So basically I watched this video and then I had to go and attempt a remote viewing. Let me turn this down a little bit.
If you looked at a movie,
Look at that.
neural activity with neurons spiking here and here and here and here, it's very difficult, if not impossible, to detect any pattern in the firing. But when you look at this pattern of firing through the filter of algebraic topology,
the filter of algebraic topology, which I never heard of until I looked at this video, and it wasn't even in the description or anything like that. Algebraic topology is a branch of mathematics that uses tools from abstract algebra, which I'm going to really look into, to study topographical spaces. The basic goal is to find algebraic invariance, property of a mathematical object which remains unchanged after operations or transformations of a certain type are applied to the object. That classify topographical spaces up to homeomorphism. Some of these I just don't understand, though usually most classify up to whatever that means. I don't even know what that means. Topological spaces. So that was an interesting word, topological spaces. In mathematics, a topological space is, roughly speaking, a geometric space in which closeness is defined but cannot necessarily be measured by a numeric distance. This is very important. It's very important in remote viewing, in our understanding or the comprehension of dimensional spaces or dimensional sensations. More specifically, a topological space is a set whose elements are called points, along with an additional structure called a topology, which can be defined as a set of neighborhoods for each point that satisfies some axioms, formalizing the concept of closeness. It's a very complicated way of... I like the way they're writing though. Closeness is a basic concept of topology and related areas of mathematics. Intuitively, we say two sets are close if they are arbitrarily near to each other. The concept can be defined naturally in metric space, where a notion, which I love that word notion, a notion of, this is one of my favorite words that I apply to remote viewing, notion, where a notion of distance between elements of the space is defined, but it can be generalized to topological spaces where we have no concrete way to measure distance. This is remote viewing is the same thing. So here's, as I'm watching this video and I'm listening to her talk about this, and I'm looking at these images of the brain. Let me just go through this real quick.
neural activity with neurons spiking here and here and here and here, it's very difficult, if not impossible, to detect any pattern in the firing. But when you look at this pattern of firing through the filter of algebraic topology, different structures emerge in terms of which families of neurons are firing in which order, and then more complex structures when you look at how these different families are related to each other. When one looks at the evolution of such a pattern through time, it gives us a mathematical signature that describes this pattern that was hidden in the seemingly chaotic firing of the network. The big question is, you're looking at the brain after a stimulus.
Stimulus is a range of time and space.
It has this activity pattern, and somehow it should
Boom, that's where it comes in. This is what the neurons look like when an actual remote viewing is taking place.
be encoding information about what came in and then coming to some sort of decision about what to do next.
Right.
What I think that we're seeing here is a way of interpreting or visualizing the brain's own code for what it's doing. It processes the information, it's encoding the input signal, and then it's coming to some sort of decision.
Mm-hmm.
And what algebraic topology enables us to do is to describe that encoding process and perhaps even to visualize the moment at which the brain is making a decision. So there are more and more intricate structures among these neurons that are building up as it's thinking about, it's processing the information, and then boom, we come to a decision. Whoop! And that's what we're detecting. We're detecting the information processing and decision-making processing of the brain.
Mm-hmm. Yeah. Now what I'd like to have is some kind of technology that can actually record this, just like this here.
They're looking at the brain after a stimulus, and it has this activity pattern, and somehow it should
like
be
that, like that. Now imagine, this is what I was thinking about earlier too, is now obviously this is a graphic. It's not real, but if this was real, and these were real neurons, the mossy fibers, say, in the dentate gyrus, and as the stimulus comes through, or the range of time and space in whatever state it exists in, is acquired. Well, okay, all right, fine. In the attractor mechanism, fine. Mossy fibers. The speed at which that stimulus is moving through the neuron, through these fibers, as the input is making its way through. But here is an example. So I'm thinking about all this, and like, oh, okay, I gotta go and do one now, because I'm thinking about this, and that's usually when the good stuff happens. I go and I get inspired, and I go and do some work. So in this process, this is what I'm thinking about. I'm thinking about trying to contemplate this. This is dimensional sensations here is what they're talking about. Closeness, or the mathematical concept of closeness. That's what I call dimensional sensations, or the use of proprioception, where you're at in space, but if the proprioceptors have something to define the space. If there's nothing to define the space, then we go with the notion, that's why I love the word notion, of distance between elements. So let's look at the example here. This is the range here. Focus on focused. Couple things that I'm doing here. First, again, I'm going back to the inspiration. Excitement from seeing this. Then I'm bringing my awareness that, oh, there's a range of time and space. I have to go there, or acquire that, and I want it to go through this part of my own brain. That's what I want. So there is shape. There's stones, or it's a notion of stones or the side of a mountain or a cliff. Very basic. All right, now I'm going to go and see if there's anything else I can get. I get this side here. It has the quality of this matches this right here. The steepness right here matches with the quality of this, and I don't need to do any more. And I'm done. I don't have to do any more. This goes back to what she's talking about in this algebraic topology conversation about when the brain makes a decision right here. And that's what I'm doing here as well. I'm making the decision on that, and then I make a decision on that based on the quality. This had a certain quality, this had a certain quality. I make the decision, and then I'm done. I don't fully understand this algebraic topology because it's brand new to me as of like 20 minutes ago, but I'm going to do my best to try to get a better idea of what this means, because it fits into what I call dimensional sensations, or a notion of distance between elements of the space. All right, many more to come.